All right, hey Stat 113 people. I'm on page 5 of our second little note packet here, and we're going to pick up talking about what these first and third quartiles are, and we're going to end up using them for one of our measures of spread. And so the main purpose of this video will be to talk about measures of spread in a numeric variable, what that exactly means. And stuff like that. And so our first quartile, we're just going to think about that as if we order all of the numbers of a variable, so like all of the home runs. Then this first quartile, which is often abbreviated as Q1, is the number that separates the bottom 25% from the upper 75%. So going back to that like time you can run a mile analogy, if your time was the first quartile, then that means that your time was larger than a fourth of the class and smaller than 3/4 of the class. And so kind of corresponding to this is this third quartile. So if you order all numbers, then Q3, it's pretty much just like the opposite of this. So it's the number that separates the bottom 75% from the upper 25%. And so these numbers are really just kind of given just to kind of give you a brief kind of summary or idea about what this distribution of a numeric variable is going to look like. And so they don't provide everything, but it does give us some information to know that, okay, 25 or about 25% of the baseball players in this data set actually hit fewer than 3 home runs. So a kind of a large chunk, a fourth of them, aren't even really getting past 3 home runs. And then you could make kind of the same type of logic about Q3, except we're saying that about 25% of the baseball players in this data set actually hit more than 16 home runs. So a fourth of them hit quite a few home runs, more than 16. And so this is going to lead us into our measures of spread. So we won't see these right away. We'll see them in our second measure. But spread, you could just kind of think about how spread out these data points are on the x-axis. And so something with more spread is going to have kind of a longer x-axis with more of the points kind of spread out. Something with less spread than this is going to kind of smush a lot of these data points together so that the x-axis kind of gets smushed. So we'll see some examples of this, but we're going to go ahead and define a few things that are going to help us calculate measures of spread. And so the first is just going to be a deviation. And so a deviation is just the distance of an observation from its mean. So in our baseball example, let's go ahead and calculate some of these deviations. So remember, our mean was 10.17. We're getting that from our table. And so each observation is going to have its own deviation. And so the first home run value was 6. So the deviation of the first observation I'm just going to call it deviation 1, is going to be 6 minus 10.17. That's going to give us the distance of the observation from its mean, so negative 4.17. We're going to let the deviations be negative. That indicates that the observation was less than the mean. Deviation 2 could just come to the next observation in the data set. That's going to be 10. So deviation 2 is 10 minus 10.17. So we get negative 0.17. So deviations have units, and so in this case it's runs or home runs really. And then just kind of keep in mind that there will be 436 deviations. So each player has their own deviation. It could be negative if they hit less than the average number. It could be positive if they hit more. We're going to use these deviations. You could kind of reason out that a variable is going to have a larger spread if its deviations are larger, because that's going to indicate that a lot of observations are farther away from the mean. And so we're going to end up using these deviations in the variance. And so the variance is going to let us condense all 436 of these deviations down to just a single number. And so how we're going to calculate it is we're going to square all of the deviations, add them up, and then divide by the sample size minus 1. And so in our example, what that would look like is, let's see, so first we're going to square our deviation. So I'm going to take negative 4.17 squared. And then we're going to add them up. So that means I've got to do negative 0.17 squared. And then you keep doing this over and over and over and over and over again. So obviously that's like a huge pain. We're never actually going to calculate that by hand. And then once you do all that, we're going to divide by 436 minus 1. Okay, so hopefully it makes some intuitive sense that larger deviations are going to lead to a larger this thing. So larger deviations are going to lead to a larger variance. What we're actually going to use is a standard, the standard deviation. And so the standard deviation, at least this is easy. This is just the square root of the variance. So you calculate this mess, and then you just take the square root. That's the standard deviation. We're only kind of bothering with that because the standard deviation has this like nice interpretation. And so it's thought of as the typical deviation of an observation from the mean. So it's kind of thought of like, okay, on average, how far is an observation going to be from its mean? A larger value of a standard deviation then is going to indicate higher spread, because that means observations are going to be farther from the mean. A smaller value is going to indicate a smaller spread, and that's going to indicate that deviations are kind of small, so they're going to be like super, super close to the mean. All right, so variance and variability is kind of one of the harder concepts, so if it doesn't click right away, definitely be patient. We'll come back with the next video talking about an example that should hopefully kind of make things a little bit clearer.